We start with first in the series of 3 lectures that will be given by Kurt VINHAGE on fundamentals of partially hyperbolic abelian group actions.
Thank you very much for being here. I know it's the afternoon of the first day, and several of us traveling, including myself, are rather wiped out. But hopefully we can get through the fundamentals today and get to the more interesting stuff on Wednesday. So what do I want to talk about? I want to talk about partially hyperbolic abelian group actions to start. So the setting here is going to be that alpha is an action of an abelian group, RK cross ZL, on a manifold X. Let's just assume that it's by C infinity diffeomorphisms. And just so that I have an orbit foliation for the RK part, I'm going to assume locally free. So I need to tell you what I mean by a partially hyperbolic abelian group action. And I'm going to start with a single distribution first, which I want to distinguish. So fix a distribution EC on X, right? So this means that EC of X is a subspace of the tangent bundle to X at X for every X of the same dimension. And I want to say that an element A in RK cross ZL is EC partially hyperbolic if it has a dominated splitting. So I want there to exist subbundles, a stable bundle for the diffeomorphism A. So I'm going to use the subscript to denote which diffeomorphism I'm looking at. And EUA in the tangent space, which are also distributions, such that this splits as a stable plus central. Notice that the central doesn't depend on A, and this is going to be important. And the unstable is and here I just want A invariant dominated splitting. With EC can contain the orbit direction, or will contain the we will be forced to contain the orbit direction if this is true. So I want ESA contracting and EUA expanding. So this makes sense, right? I have a fixed distribution. I can start looking at different elements and ask whether or not one of these elements is partially hyperbolic with respect to this distribution. If, to address Amadeus's point, the central distribution is the tangent space to the orbit for the RK part, so these are the RK orbits, we call the action an Nosov. We call A an Nosov. So this is actually a fairly familiar definition when K and L are low, right? So if I have K and L being 1, 0, this is the definition of an Anosov flow. Or a partially hyperbolic flow. And if K and L is 0, 1, this is an Anosov diffeo, or more generally, a partially hyperbolic diffeo. So one of the nice structural things, and I want to start looking at the set of these uniformly hyperbolic elements, these partially hyperbolic or Anosov elements. One of the immediate things, just in the case of an Anosov flow, you can check that, you only need to check that one diffeomorphism is Anosov. And just like in Anosov diffeo, I only need to check that the generator is Anosov. Once I have that one element is Anosov, every element is Anosov. This isn't true anymore in this setting, but we have some structure to the set of uniformly hyperbolic elements. This is the first lemma, which I'm going to leave as an exercise, because it's the proof is the same as in the rank 1 case. So if A is in RK cross ZL, is Anosov or EC partially hyperbolic, and TA is also in RK cross ZL, then so is TA, right? TA is Anosov or partially hyperbolic with respect to the center, right? If T is bigger than 1, this is rather easy, right? Because I'm taking a larger iterate. So, right, if I see expansion now, I see expansion later. It's when T is less than 1 that you have to worry. And this is also not too bad. Yeah. T is T is a real number. Minus 0. It can be negative, right? It's just going to swap the roles of stable and unstable. But it can be a real number. It's not too bad. I'm asking you to trust me. If there's demand for this, I'll prove it next time. But it's first prove that if the time t map of a flow is partially hyperbolic with respect to the orbit, then that flow is Anosov. This is not so bad for locally free flow. (0.5) TA. All right, so I'm assuming that this A is Anosov, and then I'm also assuming that the rescaling is also part of the group. Right? Yeah, so this contraction and expansion rate can vary with A, right? So
Can be as small as
that's something we'll come to exactly. It could be very, very small. And in fact, it will have to be very, very small, as we'll see very shortly, for certain iterates. So what do we want to do? We want to do all the things that we like to do in hyperbolic dynamics, but with respect to this group action now. And so we want to build things like stable foliations, which we can do. So the first topic here is common stable foliations. The stable foliations themselves for a single element are guaranteed to exist by work of Hirsch, Pugh, and Schub. So, and I think this is overkill. Maybe someone can give me a better reference for this, because Hirsch, Pugh, and Schub Well, in the partially hyperbolic case, it's overkill, but in the it's not. But in the Anosov case, I think it's overkill. So if someone has a better reference for this, please let me know. But certainly in the partially hyperbolic case, this is the proper reference, as far as I know. So if A in RK cross ZL is Anosov or EC partially hyperbolic, then it has common stable foliation. So E star A integrates to Holder foliation with smooth leaves. Let me emphasize here that they're, yeah. Where here and here star is S or U. All right, so I have these nice foliations, and they're characterized dynamically by having the distance between points contract at the rate given by this domination. So 2 points belong to the same stable leaf for A if, when I iterate A forward, the distance between X and Y contracts at a rate faster than the lambda that separates this ES and EC. In particular, when I'm in the Anosov setting, it's exactly the set of points that contract, just qualitatively. So what do I want to do? I want to start refining these foliations, right? If we were in rank 1, we'd be done. These are the only 2 foliations we have. But in higher rank, I have ways to build new, exciting, different foliations. And it basically comes from looking at how the other elements of an action interact with a stable foliation for A. So the first thing I want to note is that if B is in RK cross ZL, dB of E star A equals E star A. So this distribution is invariant under B. So why is that true? It's because, well, this dB of E star A, this is also an invariant foliation distribution for A. Fitting into a dominated splitting. So what do I mean by this? I mean that I have, if I look at dB of ESA plus dB of EC plus dB of EUA, I claim that this is another dominated splitting with the same type of domination, and it must be the same splitting over again. So in fact, once I have a partially hyperbolic element with respect to EC, EC is not invariant just under that element, it's invariant under every element of RK. And the proof of this is rather easy, right? If I look at a vector here, this means that V is dBW which means, of course, that V, if I look at a to the n V, this is dA to the n of V. This is dB of, and here I'm using commutativity. And this decays at a rate given by the domination of A, right? It's controlled. This decays at a rate faster than the central distribution. So what ends up happening is I can look at a stable distribution for A and then look at how B acts on it. And there's no reason that B has to so look at the sequence of maps. B, which goes from the stable manifold for A of x to the stable manifold of A at Bx, which goes to the stable manifold over A at B squared x, and so on and so forth. Right, so I have here x, the stable manifold for A at x, stable manifold for A at Bx, right? And I'm just looking at how B intertwines these manifolds. Now, if B is also EC partially hyperbolic, well, this stable manifold is transverse to the central distribution. So whatever B does to this has to be hyperbolic. If B is also expanding or also contracting everywhere on this manifold for A, it's rather boring. I can't get any new information. But if B somehow splits this in another way, right, so maybe I have the stable for B and the unstable for B sitting inside of WSA, I can just run the proof of the stable manifold theorem, right? If you've looked at this proof, you might have seen it listed as just a sequence of maps, right? If I have a sequence of maps that fix the origin, that's exactly what I have here, which are hyperbolic. I have a stable manifold. So I can run the proof of the stable manifold theorem, and within the stable manifold for A, produce a stable manifold for A, intersect the stable manifold for B. And it turns out you can run this inductively. I'm sweeping some technical issues under the rug. But the upshot is the following. So if I have finitely many elements, A1 through AN, are EC partially hyperbolic or Anosov, then the common stable manifold, whose leaves are just the intersection of the stable manifolds for each, is a Holder foliation with C-infinity leaves. So this is kind of nice. Whenever you give me a list of elements, maybe I chose too many and these are redundant, but whenever you give me a list of elements, I can provide you a foliation, provided that they're all partially hyperbolic or Anosov. So what do I want to do? Well, here I drew a picture in 2 dimensions, but maybe I need to keep going down and down and down. And at each point, I can check, is there an element of the RK cross ZL action that's neither uniformly expanding nor uniformly contracting on this common stable manifold? If there is, then I can use that to pare it down, get a smaller dimensional manifold. And once I complete this process, right, I have finitely many dimensions, so this process must be completed. I end up with what I'm going to call uniform Course-Lyapunov foliations, which are going to be distinct, if you've seen this before, from the usual definition of a Course-Lyapunov foliation that I want to talk about soon. So definition, a foliation W is a Course-Lyapunov foliation if I can find A1 through AN such that W is equal to the common stable manifold of the A1s through ANs. The dimension of W is at least 1. Right, so I didn't pare down so much that I just got the trivial point, right? I could always engineer this by taking WSA intersect WS minus A. There's no point that's stable for both directions. And for every EC partially hyperbolic A in RK cross ZL, W subfoliates either the stable manifold for A or the unstable manifold for A. Right, which is just saying that it's not split across the stable and unstable manifolds for some elements. It's either always stable or always unstable.
Is the second part of the definition a consequence, or do you have to add that definition?
This? If I drop this, this is just the definition of a non-trivial common stable manifold. So this is a minimality condition, saying that I've already intersected it as much as I can. Any other questions? Sorry? Course, we'll see this when I talk about oscillated spaces in Lyapunov exponents for higher rank. But basically, in a lot of settings, this corresponds to positively proportional Lyapunov exponents. But this is, for now, it's just a definition. We call it course because it's. Say that again?
Language-wise course, you might have a finite foliation, which is still non-trivial, still invariant, but you don't want to consider.
Exactly. So this could be, this isn't a Lyapunov foliation because if you fix an invariant measure, the oscillated spaces here for a given element could have invariant Lyapunov subfoliations. So I'm not conformal on each one. And I should add the word uniform here to emphasize the difference between my definition and sort of the standard one. Let me go through a few examples because this is a bit tricky without examples in your head. So what are the two examples I want to take? The first example I want to take is a product. So alpha is the product of two flows, psi t cross phi s. And I want psi t and phi s to be in Hausdorff flows. So what are the Course-Lyapunovs? The Course-Lyapunovs are the stable and unstable foliations for psi t and phi s. So E sub SU for psi. I guess I'll use W to, and WSU for phi. And why is this true? Because, well, we need to figure out what the Anosov and partially hyperbolic elements are. The Anosov elements are exactly the R2 minus the axes, right?
Sorry, Kurt?
Mm-hmm.
So they're acting on n square or acting on n? They're acting on the manifold, the square of n.
Yeah, so this is sort of acting on M, this is acting on N, and then I'm acting on the product space. Don't need to be the same dimension. So R minus the axes is the set of Anosov elements. Right? Because if I move straight up, I say I will expand the unstable of phi s, contract the stable of phi s, but I'll be neutral on psi t, right? I'm not doing anything in the manifold M. All the points are fixed on M. So this is partially hyperbolic with respect to a larger central distribution, which is the theme that we'll see on Wednesday's talk. But it's not an Anosov. But if I take sort of a generic element here, the stable manifold is going to be the stable manifold plus the stable manifold. So this is E stable psi plus E stable phi. If I go down here, well, now I'm moving down, right? So the things that are contracted here are going to be, it's E stable psi plus E unstable phi. And the intersection of these two give me the stable of psi. Sort of using each of these quadrants, I can get what I want, right? So this switches the other one, so it's E unstable psi plus E stable phi. And then both of these are unstable down here. Notice that the key feature of this example is that the set of Anosov elements are dense. In fact, they're a complement of hyperplanes, which we'll see is equivalent to density pretty soon. Let me give another example. Which is the Wall chamber flow on SL3R. So this is another R2 action. I have a preference for R2 action, so I always write things in as R2. So I take a co-compact lattice in SL3R. I take the quotient space by this co-compact lattice. And I look at the action of the diagonal subgroup by left multiplication. So alpha of T1, T2, acting on G gamma, is just going to be e to the T1, e to the T2, e to the minus T1 minus T2, G gamma. Now it turns out that this action is an Anosov. The diagonal subgroup, the orbit subgroup, is the only thing that's neutral. Everything else sort of, if you are familiar with SL2R mod gamma, right, the reason that you get expansion is that the rate of expansion or contraction is given by conjugation, right? So if I multiply on the left by e to the t1, and at the right by e to the minus t2, this expands at the rate e to the t1 minus t2. This is a phenomenon more general to semi-simple Lie groups. But for this specific example, these elementary subgroups, which are invariants by conjugation of the diagonal subgroups, form the Course-Lyapunov distributions and integrate to actually homogeneous Course-Lyapunov foliations. So the Course-Lyapunovs are the foliations Wij of x, which is the orbit of this unipotent subgroup, where I look at the ijth coordinate and multiply by x. But the stables are much bigger. The stable foliations are all three-dimensional. So what's the upshot here? Why do I like this so much? Well, instead of just having two foliations, I have many. And unlike the usual notion of a Lyapunov foliation in when I have an invariant measure, these are actually still Holder foliations with smooth leaves, right? They're not these measurable, yucky things that we have to worry about them degenerating at some points, because the oscillated splitting is only measurable. So the Course-Lyapunovs are always as good as the usual stable foliations. All right, any questions about Course-Lyapunov foliations? Yeah?
In the third quadrant there, should it be U?
Yeah, it should be UU, thank you. So I pick a pair of distinct numbers between 1 and 3, ij. So, right, so e.g. W12 is this group. It's a unipotent subgroup. It acts a lot like a Hoare-cyclic subgroup. Star is in R, is any real number. Yeah. Yeah, I mean, I can, I don't know off the top of my head, but you can take two commuting 3x3 matrices on T3, the type that Amy talked about this morning, where you have three distinct real eigenvalues. It always has something commuting with it that also has three distinct real eigenvalues and is not a power of it. And this is going to generate something like this. It's not so easy. Some people who work with this know the examples off the top of their head. I'm not one of those people. So, any other questions? You can, of course, just take a product action for Z too, right? I can take a hyperbolic toral automorphism cross a hyperbolic toral automorphism. So now I want to specialize to RK. And I'm secretly not cheating at all by a construction called the suspension, but I don't want to focus too much on suspensions today. So and what I want to do next is talk about how does the set of EC partially hyperbolic elements look. And it turns out to have a very nifty description, or at least characterization. So definition, an open convex cone in RK is an open subset C such that for all t bigger than 0, Tc equals C, right? So it's invariant under positive scalar multiplication. And also C is convex. So it's invariant under convex combinations, and because it's also invariant under rescaling, it's actually invariant under all positive linear combinations as well. So a symmetric open convex cone is a set of the form C union minus C. So I take the opposite cone, and I just take its opposite, right? So it might look something like this. This is C, and then I take minus C as well. So what do I want to prove? I want to show that the set of partially hyperbolic elements is an intersection of finitely many open convex cones. Notice that half spaces are open convex cones. They're sort of the biggest ones you can get in this context. So the first thing we need to prove, I need one more definition, sorry. So let C minus W be the set of all A's such that A uniformly contracts W. And I don't specify the contraction rate. It could be very, very weak. And the lemma is that C minus of W is an open convex cone. Right, so invariance under positive scalar multiplication is something that I mentioned at the start, right? That if I have an Anosov element, every scalar multiple of that Anosov element is also Anosov, and the same is true here. So I'm going to prove, well, I'm not even going to write the proof, right? It's rather straightforward. If I have two elements that both uniformly contract W, and I start applying the sum of them, or a convex combination of them, because everything's abelian, I can rearrange them to just apply an iterative A and then an iterative B. So because everything is invariant under rescaling, I still get a kind of contraction on W for any positive linear combination even. So what's the upshot? the main thing you get is that the set of partially hyperbolic elements, let me call it pH of EC. So this is the partially hyperbolic elements with respect to EC, the EC partially hyperbolic elements, is the intersection over all W of coarsely up enough foliation of C minus W a union minus C minus W. Right, because an element will be partially hyperbolic if and only if for each of these coarsely up enough foliations, it's either expanding or contracting. And I can build the stable foliation by taking all the ones that it's stable for, and the unstable foliation by choosing all the one that it's unstable for.
But not as fast.
So I was thinking about the Anosov case here, but of course, yes. So uniformly contracts W faster than EC. That's a good point. All right, any questions about this? I go till 10, yes? 10 after. Okay. I think I tried to bite off more than I can chew with my notes, so I'm going to skip the Anosov closing lemma. Suffice it to say, you still have a lot of the features of hyperbolic theory in the case of Anosov actions. You just need to be careful that you have enough expansion and enough contraction. So you can look at the set of, and this is where the rate of domination comes in, right? I can look at C minus, and I can insert a lambda here and ask that it's faster than lambda. And in the Anosov case, as long as the action returns to itself very close to where I started, with enough domination, it can be closed up not only to a periodic orbit, but an RK periodic orbit. It's a k-dimensional torus, which is kind of surprising, because it's not immediately clear that just because I close up once, I close up in every other direction. But uniform hyperbolicity allows for this to happen. And if you're interested, I'm happy to talk after the first lecture. Yeah?
Those ones have a sort of flat boundary?
Yeah, I don't know.
Can it be like an ice cream cone?
Yes, I expect that in several examples it's like an ice cream cone. So it could look like, right, if I have an R3 action, it could look like this. And I take out this, and everything outside of this will be the partially hyperbolic elements. I think there's a lot of questions to be answered about what these things can look like. So what do I want to do? I want to make one more definition, which will be useful on Wednesday, and then talk about the two things that I want to talk about, one on Wednesday and one on Friday. So, definition, alpha is called totally partially hyperbolic. Or totally Anosov. if the set of uniform elements, let me write it like this, PHEC is dense in RK. And this happens for quite a few actions. For ZL, so when we have a ZL components, we want projectively dense. So when I project everything's invariant under rescaling. So I can really just think about it as the set of directions. So the set of directions that are in Asaf, I want to be dense on the sphere when I project them down. Does that make sense? Right, so I want to consider, say, the product of two Anosov diffeos to be a totally Anosov Z2 action. But of course, it doesn't make sense to say dense because it's a discrete set. And the only two directions that are not Anosov are the exact horizontal direction and the vertical direction. So the only two directions on the sphere, when I project Z2 onto the sphere, that are not Anosov are the axes. It's a foliation. So I'll get into that probably on Wednesday. In all of the examples previously known, and this is something else I was hoping to get to today, but I've only got 3 minutes, and I want to be kind to my fellow Utahn and end on time. But sort of in homogeneous examples, let's talk about this. W, which is the sum over all chi, which are positively proportional to some chi naught, E chi, is, of course, the Lyapunov foliation. So one of the other things I hope to talk about and had planned too much, I think, was that in higher rank, the Ossoledet's theorem tells you that the rates of expansion and contraction are actually functionals on RK, or ZL. So, right, we took away the axes, and these were the kernels of certain functionals. And in general, two things will sort of have the same set of expanding elements if they're positively proportional. So positive proportionality of the exponents is why these are called, of course, the Lyapunovs. So what's the plan? The plan is to go in two different directions. So on Wednesday, we're going to look at, with the assumption of totally partially hyperbolic, we're going to get a lot of rigidity. And in the other direction, on Friday, we're going to look at non-totally partial hyperbolic actions. And these have a lot of exotic phenomenon. In particular, I want to emphasize the link between systems that are K but not Bernoulli. Okay, I'll stop here.
Questions?
Is totally partial hyperbolic the same as totally anosov?
So totally anosov just means that EC is the orbit foliation,
Ah, okay, okay.
right? I just want the set of uniform elements to be dense.
Any other questions?
Assume that you have just one element which is hyperbolic. Yes, I'm thinking more
That's the
about.
definition of anosov, yes.
Yes, so quite how often it implies that actually the action is totally anosov.
So this depends on the setting. I've sort of tried to avoid today's lecture talking about the rigidity phenomenon. So usually if you have no rank 1 factor and you're one of these homogeneous systems, every perturbation is actually smoothly conjugate to the original. So totally anosov is open, right, in that. In a work in progress with a postdoc at Utah, we're proving that generically for a product, the perturbation is not totally anosov. So this is somehow a singular condition if you have rank 1 factors.
Any other questions?
But I think at some point you proved that any stable foliation is spanned by Korf-Lyapunov, right?
Yeah, it's just,
It's used in the proof of the corollary, right?
it is, yes, exactly. So right, what's one of the things I skipped over was that the tangent space splits as the EC plus the sum of all the Korf-Lyapunov foliations that are distinct, and every stable manifold is built from the Korf-Lyapunov distributions. And every unstable manifold is a sum of the expanding Korf-Lyapunov distributions.
Any other questions? Okay, if not, let's thank Kurt again.